to this video. In this video, we are going to answer one of the most interesting questions in deep learning. Can neural networks predict the future? Of course, we are not talking about magic. We are talking about sequence data. A sequence can be daily temperature, monthly sales, stock prices, power consumption, website traffic, or even words in a sentence. In all these examples, the order matters. If I give you today's temperature, that may help. But if I give you the temperature of the last 30 days, the pattern becomes much more meaningful. And this is exactly where sequence models become important. In this video, we will build the story step by step. First, we will see why traditional dense neural networks are limited for time series forecasting. Then we will use one-dimensional convolutional neural networks, or Conv1D, to detect local patterns in a sequence. After that, we will move to recurrent neural networks, or RNNs, and understand how they create memory. Finally, we will compare simple RNNs, LSTMs, GRUs, and bidirectional GRUs in TensorFlow. By the end of this video, you will understand not only how to write the code, but also why these models work, when they fail, and which one you should try first for your own forecasting projects. Are you ready? Let's go.
Before we build any model, we need to understand what makes sequence data different. In a normal machine learning problem, we usually assume that each input example is independent. For example, if we want to predict the price of a house, we may use the size of the house, the number of bedrooms, the location, and other features. But in sequence problems, the current value is often connected to previous values. For example, if we want to predict next month's sales, last month's sales matter. The month before, that may also matter. And if the data has seasonality, the same month last year may be extremely important. So the model should not look at each data point in isolation. It should understand the pattern over time. This is why sequence prediction can appear in many forms. If the output is a number, like future sales or future temperature, we call it a regression problem. If the output is yes or no, like whether it will rain tomorrow, it becomes a binary classification problem. And if the output is one of many categories, like predicting the next character in a sentence, it becomes a multi-class classification problem. So sequence learning is not just about weather or stock prices. It is about any problem where the order of information changes the meaning of the data. Now let's start with the simplest idea. Why don't we just use a normal dense neural network? For example, suppose we want to predict next month's book sales. We could give the network this month's book sales, maybe this month's general sales, and ask it to predict next month's book sales. This sounds reasonable, but the problem is that the network receives very limited information. Sales data is often seasonal. Maybe December is always higher because of holidays. Maybe summer is always lower. Maybe there is a yearly pattern. If the network only sees the current month, it cannot discover those patterns. So the next idea is to give it more history. Instead of 1 month, we give it the last 3 months, or the last 6 months. This is better. But now we have a new problem. How much history should we include? If the window is too short, the model misses important patterns. If the window is too long, the input becomes larger, training becomes harder, and the model may overfit. Also, the important event may happen outside the fixed window. So dense neural networks can work for simple cases, but they do not naturally remember the past. What we really want is a model that can learn what to remember by itself. And this is where sequence models come in. Before we jump into RNNs, let's start with the model that many people associate with images: convolutional neural networks. Convolutions are famous in computer vision. In images, a two-dimensional filter slides over pixels and learns to detect local patterns such as edges, corners, curves, and textures. But the same idea can be used for sequences. The only difference is that instead of a two-dimensional convolution, we use a one-dimensional convolution. So instead of sliding over height and width, the filter slides over time. Let's look at a simple numerical sequence. Imagine we have these values. Now we apply a small one-dimensional filter with 3 values shown in the picture. This filter looks at 3 neighboring values at a time. For example, when it looks at 4, 8, and 15, it calculates 4 times -0.5 plus 8 times 1 plus 15 times -0.5. The result is -1.5. Then the filter moves 1 step forward. Now it looks at 8, 15, and 16. Again, it applies the same calculation and produces a new value. This is the key idea behind one-dimensional convolution. To combine the code and the concept in this video, let's start with the simplest possible forecasting problem. Imagine we have a one-dimensional time series, such as daily sales. Each number represents the sales value at one time step. At this stage, we keep the problem simple. We only have one feature, which is sales. So this is a univariate time series. Our goal is to use the previous values to predict the next value. But before we build a one-dimensional convolutional model, we need to understand one of the most important concepts in time series forecasting: windowing. A neural network cannot learn directly from one long list of numbers. We need to convert this raw time series into input-target pairs. For example, if the window size is 3, we give the model 3 previous values and ask it to predict the next value. This is called sliding windowing. The window moves one step at a time across the series. In this simple example, the target is the next single value. This is called one-step forecasting, but the target does not always have to be one value. For example, we can also use 20 past values to predict the next 2 values. That would be multi-step forecasting. In newer version of TensorFlow and Keras, we can use a built-in utility to apply windowing on our NumPy array. Let's understand this line by line. First, here, it means we use the series as input, but we remove the last value. Next, np.newAxis adds one extra dimension. Originally, the data looks like this. After this line, it converts into this. This line means the target starts after the first window. Then sequence length equals window size tells Keras how many time steps each input window should contain. And sequence stride equals 1 means the window moves one step at a time. Setting shuffle equals true means that after the input windows and their corresponding targets are created, they are not fed to the model in the same order as they appear in the original time series. Instead, the training examples are randomly shuffled before each epoch. This prevents the model from relying on the order of the training samples and usually helps it generalize better. Notice that we are not shuffling the values inside each window. We are only shuffling the windows themselves. So this function converts a raw time series into supervised learning examples. This is the key point. Windowing converts a time series problem into an X to Y learning problem. Now that we have a windowed data set, we can build a one-dimensional convolutional model. Now let's understand the one-dimensional convolutional layer. Filters equals 128 means the model learns 128 different filters. You can think of these filters as 128 small pattern detectors. At the beginning of training, these filters are just random numbers. During training, backpropagation gradually adjusts those numbers to reduce the prediction error. Eventually, some filters may become sensitive to short upward trends. Some may become sensitive to sudden drops. Some may detect local peaks. Some may detect small cycles or fluctuations. We do not manually program these patterns. The model learns useful filters automatically by minimizing the loss. Note that we determine the size of filters by kernel size. Window size controls how much history the model receives. Kernel size controls how much of that history each filter sees at one time. A larger kernel size is not necessarily better. Small kernels are often better at detecting local patterns, while larger kernels can capture broader trends and seasonality. Choosing the right kernel size is a trade-off, and should be treated as a hyperparameter. Similarly, a larger window size gives the model more historical information, but it also increases complexity and the risk of overfitting. The window should be large enough to capture the longest meaningful pattern in the data, but not unnecessarily larger. A good rule of thumb is to choose a window size that is large enough to cover the longest meaningful pattern in your data. For example, if your data has a weekly pattern, start with a window size of 7 to 14 days. If it has a monthly pattern, start with a window size of around 30 to 60 days. The goal is to give the model enough history to observe at least one full cycle of the pattern you want it to learn. Once the window size is chosen, the kernel size should usually be much smaller than the window size. A common starting point is between 10% and 30% of the window size. Smaller kernels focus on short-term patterns such as spikes, dips, and local fluctuations. Larger kernels capture broader patterns such as trends, seasonality, and longer cycles. After the conv1d layer extracts local patterns, the dense layers combine those extracted features, and produce the final prediction. In most forecasting problems, the windowed version performs much better because the model receives temporal context instead of isolated individual values. However, the improvement depends on the data set. If the next value depends only on the current value, a simple non-windowed model may still work reasonably well. But for real-time series with trends, seasonality, and temporal dependencies, windowing is usually essential.
Now let's move to recurrent neural networks. A recurrent neural network looks similar to a feed-forward neural network, but with one major difference. It has a connection pointing backward. That backward connection allows information from the previous time step to influence the current time step. Let's start with the simplest possible RNN. At time step t, the recurrent neuron receives two things. First, it receives the current input, x of t. Second, it receives its own output from the previous time step, y of t minus 1. At the very first time step, there is no previous output, so we usually initialize it with 0. Now, if we draw this network across time, it looks like the same neuron repeated again and again. This is called unrolling the network through time. This picture is extremely important. It may look like we have many different neurons, but actually it is the same recurrent neuron reused at every time step. The weights are shared across time. This means the network can process sequences of different lengths while applying the same logic at each time step. And because each output depends on the previous output, the network has a form of memory. This memory is usually called the hidden state. The hidden state carries information from the past into the future. So when an RNN makes a prediction at time step t, it is not only using the current input, it is also using a compressed representation of what it has seen before. This is the main difference between a dense network and an RNN. A dense network receives a fixed window of values. An RNN processes the sequence step by step and updates its internal memory as it moves forward. This is why RNNs are naturally suited for sequence data.
RNNs are flexible because the input and output can have different shapes. The first case is sequence to sequence. Here, the model receives a sequence and produces a sequence. This is useful for time series forecasting when we want a prediction at each time step. The second case is a sequenced sevector. Here the model reads the whole sequence and produces one final output. For example, in sentiment analysis, the model reads an entire movie review and outputs one sentiment score. The third case is vector to sequence. Here the model receives one input and generates a sequence. A classic example is image captioning, where the input is an image and the output is a sentence. The fourth case is encoder-decoder. The encoder reads the input sequence and compresses it into a vector representation. Then the decoder uses that vector to generate a new sequence. This is the basic idea behind many translation systems. For our video, the most important case is sequence forecasting. We give the model historical values, and we ask it to predict future values. Now the next question is, how do we train an RNN? The answer is called backpropagation through time, or BPTT. We won't go too deep into mathematics of BPTT. In practice, TensorFlow and Keras handle this automatically. Let's focus on the red path shown in the figure. During backpropagation through time, if we want to compute how much the loss changes with respect to weight W1, we end up with an expression like the one shown here. Before discussing the result, let's clarify the notation. The subscripts identify different weights in the network. The superscripts in parentheses represent time steps. To keep the mathematics simple, let's assume a linear activation function whose derivative is equal to 1. This allows us to focus only on the effect of the recurrent weights and ignore the contribution of the activation function. Notice that the gradient contains a long chain of multiplications involving the same recurrent weight. This happens because, during backpropagation through time, the error does not only travel backward through layers, it also travels backward through time. Now imagine that the recurrent weight is smaller than 1. Multiplying a number smaller than 1 by itself hundreds or thousands of times makes it approach 0. As a result, the gradient gradually disappears. When this happens, the model may still learn short-term patterns, but it fails to learn information that is far away in the sequence. For example, in text, the meaning of a word may depend on a word that appeared much earlier. This is called the vanishing gradient problem. On the other hand, if the weight is larger than 1, repeated multiplication can make the gradient grow exponentially, leading to the exploding gradient problem. A simple RNN does have memory, but in practice, that memory is often short. So we need a better memory mechanism. This is where LSTM and GRU come in. LSTM stands for long short-term memory. The main idea of LSTM is to give the network a more controlled memory system. A simple RNN mixes everything into one hidden state, but an LSTM has a separate memory path, often called the cell state. You can think of the cell state as a highway that carries important information through time. The LSTM decides what should stay on this highway and what should be removed. It does this using gates. A gate is basically a mechanism that outputs values between 0 and 1. A value close to 0 means, block this information. A value close to 1 means, let this information pass. The first gate is the forget gate. It decides how much of the previous memory should be kept. If some old information is no longer useful, the forget gate can reduce its effect. The second gate is the input gate. It decides how much new information should be added to the memory. So the model does not blindly store everything. It learns what is important enough to remember. The third gate is the output gate. It decides how much of the internal memory should be exposed as the output of the cell. This gated structure is the reason LSTMs can handle longer dependencies than simple RNNs. They do not completely solve every long sequence problem, but they are much better at preserving useful information over time. That is why LSTMs became one of the default choices for sequence modeling for many years. GRU stands for Gated Recurrent Unit. A GRU is another gated recurrent cell, but it is simpler than an LSTM. The main idea is similar. Use gates to control what information should be remembered and what information should be updated. But GRU simplifies the architecture. Instead of keeping two separate state vectors like LSTM, GRU merges the memory into a single hidden state. It also uses fewer gates. In many practical problems, GRUs perform similarly to LSTMs, while being simpler and sometimes faster to train. So when should you use GRU? If you want a strong recurrent model but you want something simpler than LSTM, GRU is a very good choice. In many projects I would try both LSTM and GRU and compare their validation performance. There is no universal winner. The best model depends on the dataset, the sequence length, the amount of data, and the forecasting horizon. Now let's build our first simple RNN model for time series forecasting. We start by creating a noisy sine wave. This will simulate a real-world time series where the underlying pattern exists, but noise makes prediction more challenging. Next, we prepare the data using TensorFlow's time series dataset from array function. This automatically performs windowing for us. In this example, the window size is 50. That means the model sees the previous 50 values and tries to predict the next value. One important thing to understand is the shape of the input data. Recurrent neural networks expect data in the form samples, time steps, and features. For a univariate time series, we only have one feature, so the shape becomes something like batch size, 50 time steps, and one feature. That's why you'll often see code like this. This simply adds the feature dimension required by the RNN. Now let's look at the model. The first layer is a simple RNN with 20 units. Notice that return_sequences equals true is enabled. Why? Because another recurrent layer comes after it. The second RNN layer expects a full sequence as input, not just the final output from the previous layer. If we removed return_sequences equals true, the first layer would only return the last time step, and the second RNN would not receive the sequence it needs. Another important parameter is input_shape equals none and 1. The value none means the model can accept any number of time steps, and the 1 indicates that each time step contains one feature. Finally, the dense layer produces the prediction. In this example, dense 1 predicts the next single value in the series. If we wanted to predict the next 10 values at once, we could simply replace it with dense 10. And remember, simple RNN is only one option. In real-world applications, we often replace it with LSTM or GRU layers, which are better at capturing longer-term dependencies in the data.
And that's a wrap for this video. Today, we explored how sequence models work, why windowing is essential for time series forecasting, how Conv1D learns local patterns from sequential data, and how recurrent neural networks process information through time. We also discussed the challenges of vanishing and exploding gradients, and saw how LSTMs address these problems, using their memory cell and gating mechanisms. I hope this video helped you build an intuitive understanding of these concepts, not just memorize the equations. If you enjoyed this video and found it useful, please consider subscribing to the channel. It really helps support my work and motivates me to create more content like this. Thank you for watching, and I'll see you in the next video, where we'll continue our journey into deep learning and sequence models. Until then, happy learning.